In this lesson about inferences and dependent samples, we're going to learn how to do hypothesis testing when we have matched pairs. We will also look at a formula to help us set up a confidence interval estimate for dependent samples. So we will be using methods for testing hypotheses and constructing confidence intervals involving the mean of the differences of the values from two dependent populations. With dependent samples, there must be some relationship where each value in one sample is paired with a corresponding value in the other sample. For example, each pair of sample values consists of two measurements from the same subject. Like we could take the weight of a freshman student in September and then we could measure their weight in April. Each pair of sample values could also consist of a matched pair. For instance, we could look at the body mass index or BMI of a husband and the BMI of his wife. Here's some notation for dependent samples. Our objective is to test a claim about the mean of the differences from dependent samples. Lowercase d is the individual difference between the two values in a single matched pair. Mu sub d is the mean value of the differences d for the population of all pairs of data. This is going to be the notation that we will use for our hypotheses. D bar is the mean value of the differences d for the population of all pairs of data. S sub d is the standard deviation of the differences d for the paired sample data. N is the number of pairs of data. So the requirements for testing a claim about dependent samples are: first, the samples must be dependent. Second, the samples are simple random samples. Third, either or both of these following conditions are satisfied. The number of pairs of sample data is large, n is greater than 30, or the pairs of values have differences that are from a population having a distribution that is approximately normal. The p-value method of hypothesis testing and the traditional method of testing and confidence intervals all use the same distribution and standard error, so they are really equivalent in the sense that they result in the same conclusions. You have to have a statistical program or a graphing calculator to find exact p-values. So we are going to use the traditional method of hypothesis testing. This is also sometimes referred to as the confidence interval method. So the hypothesis test statistic that we will be calculating involves degrees of freedom. So degrees of freedom is n minus 1. The test statistic is a t, and it's equal to d bar minus mu sub d bar, and that's divided by the standard deviation, s sub d, and that's divided by the square root of n. So to find d bar, we subtract each paired data, and then we're going to type that list into our calculators and find the mean of those differences. Now the mu sub d bar comes from our claim, and that's always going to be a 0 for us. Next, we will find the standard deviation of the differences of the paired data. Again, that comes from typing the data in the calculator as a list and having the calculator find the standard deviation. We divide that by the square root of the total number of pairs of data, n. For example 1, we're going to look at research involving the freshman 15. A data set includes measured weights of college students of September and April of their freshman year. The table below lists a portion of those sample values. Use a .05 significance level to test the claim that for the population of students, the mean change in weight from September to April is equal to 0 kilograms. So if you are working with your notes, you'll notice that when you look at this table, the differences are not provided. So I just wanted to do that so you can understand how to calculate that. So we will have two different sets of data. So we've got the April weight, September weight, so it's a matched pair, and so this is for each student. And then what you want to do is you always take the top number and subtract the bottom number from it to find your differences. So I have 66 minus 67 is -1. So you will get negatives. It's very important to get that accurate. Now that we've got all the differences, this is what we're going to be using for the data that goes in the calculator. Now up here, the significance level is 0.05. That gives us alpha. And we're testing a claim that for the population of students, the mean change in weight, so that's mu sub d, from September to April is equal to 0. So let's go ahead and look at how to set up the claim and hypotheses once we do a requirements check. So the requirements are that the samples are dependent, and in this situation they are because the values are paired with each other and each pair is from the same student. Also, this was from a simple random sample, so that was indicated in the original journal that published this. And a graph of the data in the journal showed that the data has normal distribution. So we did have a small sample, but as long as you have an approximately normal distribution for the means of your differences, then you can go ahead and do your hypothesis test. So now let's set up the claim and hypotheses. So we say for the claim that mu sub d, so we're always going to use this notation when we're doing matched pairs, the mean of the differences is equal to 0. And that's because we were claiming that there is no weight gain. So the mean weight gain would be nothing, or 0 kilograms. Now, just like in previous hypothesis tests, the null hypothesis is always equal. So we use the same notation, the mean of the differences equal to 0. And then the alternative is either going to match the claim or be the opposite of equal. So we have the mean of the differences is not equal to 0. The next step is to calculate the test statistic. So you need to enter in the data from the differences in your calculator, and then you need to compute and do your calculations for one variable statistics. Now in your calculator, you're actually looking for x bar and s sub x. You're looking for the mean and the standard deviation of the sample. For our notation, though, we call it d bar and s sub d. D bar is the mean of the differences, and S sub d is the standard deviation of the differences. Type the data in your calculator using the 1var stats setting, and we want to know mean and standard deviation. Pay close attention to values that are negative. So from the calculator, we find that D bar is equal to 0.2 and S sub d is 2.4. So the test statistic formula has us take D bar and we subtract the claim from it. So we have 0.2 minus 0. So mu sub d will always be 0 for our hypothesis test for matched pairs. We divide that by 2.4 divided by the square root of 5. Now if you want to type this in the calculator in one step, you just ignore this part here and you would type 0.2 divided by parentheses, and then you type 2.4 divided by square root of 5, and you have to double close the parentheses and press equals. Always round this to 3 decimal places because it's a t test statistic. So for this, t is 0.186. The next step is to find the critical values. So we have degrees of freedom because we're using table A3 and we have a student t distribution. So we subtract 1 from the total in our sample. So remember, this is n is total pairs. So we had 5 ordered pairs. Take away 1 gives us 4 degrees of freedom. So we want to go to the 4th row in table A3. Now the significance level was 0.05. And remember that our claim involved equality, so that's area in two tails. So the area in two tails is 0.05, and then we want to go to the fourth row in table A3 to find our test statistic, or I'm sorry, the critical values. So doing that will give you critical values of positive or negative 2.776. Instead of finding a p-value, we are going to draw a picture to determine if our test statistic falls within the critical region. So we set up the normal distribution curve, and we're going to plot the critical values, negative 2.776 and positive 2.776. Anything that falls between those lines is the fail to reject. Anything that falls in the tails is rejection. We plot the test statistic to see which region it falls in, and we get 0.186. Now that falls in the blue region, so we're going to fail to reject the null hypothesis. So here's our conclusion. We failed to reject the null since the test statistic does not fall within the critical region. Using the wording on our flowchart, we determined that there is not sufficient evidence to warrant rejection of the claim that for the population of students, the mean change in weight from September to April is equal to 0 kilograms. Based on the sample results listed, there does not appear to be a significant weight gain from September to April. Now let's look at a confidence interval estimate for dependent samples. This is the format for a confidence interval estimate. It's d bar minus e is less than mu sub d is less than d bar plus e, where the margin of error e is calculated by taking the critical value t. So this right here is not a test statistic, guys. This is a critical value. It's the same critical value that we use for our hypothesis test. And we have the standard deviation of the differences divided by the square root of n. And remember that d bar was really your x bar. It's the average of the differences in your calculator. So we look up the critical value in table A3 and we find the standard deviation of the differences, divide that by the square root of n to find our margin of error. Now let's set up a confidence interval for estimating mean weight. Using the sample data below, we're going to construct a 95% confidence interval estimate of mu sub d, which is the mean of the April to September weight differences of college students in their freshman year. So here's the same data that we used when we did the hypothesis test. Now when we have a 95% confidence interval estimate, remember that that's a situation where we have our critical values and we have 95% between them. So the area left in two tails is going to be the leftover area under the curve, which is going to be 5% in two tails. So alpha is 0.05 when we have a 95% confidence interval estimate. So we do satisfy the requirements for this test since we already determined that. We find the degrees of freedom, which is one less than the total matched pairs. So we are on the fourth row of table A3. We also determined that the alpha is 0.05 in two tails. So we're going to get the same critical value, plus or minus 2.776. We also need to know d bar and s sub d, and we got that from typing the differences in our calculator and calculating the mean and standard deviation. So the margin of error for the confidence interval estimate is 2.776, so that's the critical value. Notice I don't put the negative, you just use the positive value. We multiply that by the standard deviation and divide by square root of 5. So here's the calculator entry. 2.776 times 2.4 divided by square root of 5 equals 3.0 is going to be the margin of error. So now let's set up the confidence interval in the correct form. D bar minus margin of error, D bar plus margin of error. So we have D bar, which is the average of the differences, is 0.2, and we're adding 3.0 and subtracting 3.0 from it. So we get an interval of negative 2.8 to 3.2. Now the way that we interpret this particular interval is this. We are 95% confident that the limits of negative 2.8 kilograms and 3.2 kilograms actually do contain the true value of the mean weight change from September to April. In the long run, 95% of such samples will lead to confidence interval limits that actually do contain the true population mean of the differences. Now this last sentence is extremely important. If your interval goes from a negative to a positive, then it is including 0, and that's very important. If the confidence interval includes 0 kilograms, then it's very possible that there is no change in weight. Okay, so for our third example, we're going to look at times and seconds that animated Disney movies showed the use of tobacco and alcohol. We're going to use a 0.05 significance level to test the claim that the mean of the differences is greater than 0 seconds, so that more time is devoted to showing tobacco than alcohol. So here's our data. And on your notes, if you printed the blank notes, you're going to have to fill in the differences. So you're going to be doing 176 take away 88, 51 minus 33, 0 minus 113, and that's how we get all of these differences here. This is what you want to type into your calculator, into your list or your data button to calculate the mean and standard deviations. Now when we look at this, alpha is going to be 0.05, and we're testing the claim that the mean of the differences is greater than 0 seconds. So the mean of the differences is mu sub d, and it's greater than 0. So that means that the first one is greater than the second one, and that's going to help us show that tobacco was showing a greater amount than alcohol. This is a one-tailed test. It's also a right-tailed test because we're using greater than. So the samples are dependent because the values are paired, and each pair is measured from the same movie. And the data set indicated that it was a simple random sample, and we were also told that the data is approximately normal, so the requirements are satisfied. So the claim is mu sub d is greater than 0 because we are claiming that the mean of the differences is greater than 0. The null is always equal, so we have mu sub d is equal to 0. And then the alternate is either going to match the claim or be the opposite of equal. So we have mu sub d is greater than 0 for the alternate hypothesis. So the test statistic requires us to find d bar and s sub d. D bar is the mean of the differences and S sub d is the standard deviation. So once we type the data in the calculator, we're going to find these values. We want to know the mean and standard deviation. So from the calculator, D bar or X bar is 50.5, S sub d is 98.223. So to be really precise, you really should go out several decimal places for the average and for the standard deviations. So here's our test statistic formula. So we have D bar is the mean of the differences, 50.5. We subtract the claim value, which is always going to be 0, and we divide that by standard deviation divided by square root of 10. So in the calculator, I would do 50.5 divided by parentheses 98.223 divided by square root of 10 and close parentheses twice. So we get 1.626 for the test statistic, always rounded to 3 places. Next comes critical values. So we take the total matched pairs, which was 10, and we subtract 1 to get 9. And so on table A3, we're going to go to the 9th row. Okay, so then the area is 0.05. That's our significance level. Now this is actually incorrect here. This should say area in one tail, So let's go ahead and verify that in table A3 and make sure we get the correct critical value for our test. So we want to go to the 9th row, and we want to find area in one tail. So 9th row, and we have area in one tail, alpha is 0.05. So we're looking at this particular column. So we go over and we get 1.833, and I only need the positive sign of that because this was a greater than test. So let's go back to that PowerPoint. Okay, so we have critical values. We only need the positive, so correct that there. Just positive 1.833. Okay, so instead of finding a p-value, again, we're going to draw a picture to determine where that test statistic is going to fall, and that's going to help us know how to word our final conclusion if we're going to reject the null or fail to reject the null. So we plot our critical value 1.833. Anything to the left of it is the fail to reject the null. Anything in the tail to the right is reject the null. Our test statistic 1.626 is just before the 1.833, so it does fall in the fail to reject region. Because it falls in that region, we fail to reject the null. So we fail to reject the null since the test statistic does not fall within the critical region. Using our flowchart, we're going to word it correctly, and we're going to reference the original claim. So there is not sufficient evidence to support the claim that more time in animated Disney movies is devoted to showing tobacco use than alcohol use. So for example 4, we're going to look at a data set involving blood pressure taken from the left arm and the right arm of the same person. So listed below are systolic blood pressure measurements taken from right and left arms of the same woman. We want to use a 0.05 significance level to test for a difference between the measurements from the two arms. So we have the right arm measurement, the left arm measurement, and we have to subtract those values to find the differences. So we're taking right, take away left, straight down and getting that, and that is going to be typed in our calculators to find d-bar and standard deviation. These samples are dependent because the values are paired and each pair is measured from the same woman. In the textbook, the problem was a simple random sample, and it was also from a normal distribution. So we have satisfied the requirements. So for the claim, we say that the mean of the differences is not equal to 0 because we're testing whether there is a difference in the means. So this right here is actually not equality. So when we word our final conclusion and that first question says, does the original claim contain equality, we would say no because it's a not equals. The null hypothesis is always equal, so the mean of the differences is 0. And then the alternate is going to be matching the claim. The mean of the differences is not equal to 0. So our test statistic, we're going to type the data in the calculator, use the 1-bar stat setting, and from the calculator, d-bar is negative 72.2 and S sub d, or standard deviation, is 9.311. So we take negative 72.2, we subtract the claim value, which is always a 0, divide that by 9.311 divided by the square root of 5. So we get negative 17.339 when we type that in the calculator, and that's our test statistic. Okay, so we had a total of 5 matched pairs, so if we take away 1, we get 4. So we want to go to the 4th row of table A3. The area in one tail, so again, or two tails again, yeah, that was a not equal. So the area in two tails is 0.05. So you're going to go to that, and that gives us the critical values plus or minus 2.776. So again, if you have equals or not equals, that is going to be a two-tailed test. If you have greater or less, that's obviously a one direction only, so that's where we want area in one tail if we're using that in our claim. Okay, so we plot the critical values, the positive and the negative sign, and anything between those is fail to reject. If the test statistic falls in either tail, we reject the null. We plot the test statistic. It's very extreme. It's negative 17.339. And because it falls within that critical region, we're going to reject the null hypothesis. If we reject it, then that's going to force us to support the alternative hypothesis. So when we reject the null, we would state in this case that there is sufficient evidence to support the claim. So did our original claim involve equality? No, because it had a not equals. Did we reject the null? Yes. So this is the wording that we use. Sufficient evidence to support the claim that there is a difference in measurements between the two arms. If you think about that, though, that's kind of a funny conclusion to make, even though our test supports that, because right arms and left arms should really yield the same measurements. So you have to be practical with statistics. It seems like that probably if it's the same person taking these measurements, maybe they're making a mistake with their calculations.